Okay. Hi, I'm Szumi, and I will talk about our formalization of Conatural numbers forming an exponential commutative Semiring. And this is joint work with Viktor Bense, but sorry. Oh, do I need to? Oh, yeah, thanks. Oh, let's just place this in. Yeah, brilliant. Thanks. So first, okay, I hope people are familiar with the inductive definition of natural numbers. We have two constructors, zero and successor. Yeah, but okay, there's another way to define natural numbers, which is to have one constructor, which takes a maybe of natural numbers. So we can represent zero as like using this constructor taking nothing and successor as taking just. But okay, we can sort of, so everything in like type theory and category theory have like dual stuff. So maybe we can like dualize this. So instead of an inductive type, we could have a coinductive type. And then, so here we have Conatural numbers. And this is how we write it down in Agda, but there are some idiosyncrasies of Agda syntax. So what it actually is that this Conat is an coinductive type with a single destructor, pred, taking a predecessor for Conatural number. So it's a function from Conat to maybe Conat. And like we say that if like a Conatural number doesn't have a predecessor, then it's like zero, and then if it has a predecessor, then it's a successor of something. You could think of something like that. So yeah. So let's look at some examples of Conatural numbers. To define values and functions involving coinductive types, we need to specify what the predecessor of the returning value is. For example, we say that the predecessor of zero is nothing because it doesn't have a predecessor, and predecessor of suck is just x. And then we see here, we can also define infinity, where we say that the predecessor of infinity is just infinity. So here we can see with coinductive types, we can define infinite structures where taking like the projection of the destructor, we still get like the same thing and goes on forever. Okay. And the goal of this project is to define the exponential commutative Semiring structure on Conatural numbers. So what is that? So we have three binary operators, addition, multiplication, and exponentiation. And also 0 and 1, that's two values. And then it needs to satisfy these equations. On the left, you see like the equations for commutative Semirings, where we plus is like associative and commutative, and also has a 0 as an identity. And same for multiplication. And there are some distributed laws. And then we also have some equations for exponentiation. And these equations should be familiar to you from like maybe high school, I don't know. But because like natural numbers also form an exponential commutative Semiring. Yeah. So now we want to do it for Conatural numbers. Okay. For the rest of this talk, yeah, I will show a naive attempt of doing this and show why it's not good. We need some better ways. And then I'll briefly talk about one way, which is to use the corecursion principle and think hardly about what the internal states of this should be. But then we'll see that this also doesn't scale very well. So next, we'll look at a technique by Niels Anders Danielsen of using embedded languages to help with this. And then the last approach is based on this method, refining it. And then in the end, we have formalized the full commutative Semiring structure, exponential commutative Semiring structure using the last method. Okay. So let's see what the naive attempt is. Okay. So we could like define addition, try to define addition. And okay, we need to specify what the predecessor of x plus y is. First, we match on the predecessor of x. So if it's nothing, that means it doesn't have a predecessor, so it's 0. Then we just return the predecessor of y. So predecessor of x plus y, or predecessor of 0 plus y is the predecessor of y. And then if the predecessor of 0 isn't 0, then the predecessor of x plus y is x minus 1 plus y. Okay, so we can get that x minus 1 from the matching on the predecessor of x. Yeah, and so far this is actually good. Agda accepts this, or yeah. So I'm doing all of this in Agda. Yeah, Agda accepts this, and so Agda is happy. But let's look at multiplication. Again, we specify what the predecessor of x times y is. And then we just match on both the predecessor of x and the predecessor of y. And if either of them is nothing, then we return nothing. So this means that if we multiply 0 on either side, then it's 0. And if neither of them is 0, then the predecessor of x times y is this y minus 1 plus x minus 1 times y. Well, if you like add 1 here, then you'll see that it should be equal to x times y. However, Agda isn't happy. It says that the termination check has failed. And why is this? So Agda implements something called guardedness for coinductive types, which means that all the recursive calls need to be under constructors. So here, this is the recursive call for multiplication, but unfortunately, it's an argument to this addition function. And addition isn't a constructor. But this function is actually good. It's just Agda's termination checking is too conservative. But so we will find some way to overcome this. And we had the same problem when we tried to prove things about Conatural numbers. For example, the commutativity of addition. Okay, it's just here's the recursive call, and there are some application of transitivity that you need to use around it. Okay. So next, we have this approach of defining good internal states. And what are internal states for coinductive types? So all these guarded corecursion can be represented with can be written using the corecursion principle, or this is also called the unfold function. So here we take a stepping function, s to maybe s. This function can change the state, and it can also terminate. And we also take an initial state s. And what this does is basically applies this stepping function repeatedly until it reaches nothing. And the connatural number that you get from this is the number of steps that you use the stepping function until it reaches nothing. Yeah. Okay. So we have so here I just show like the idea of how to define multiplication using this. So the internal state would be a pair of Conatural numbers. And then, for example, if you have 4 times 3, then first we would still like check whether either of them is 0. And then we can start with the initial state of 3, 2, so like decreasing each of them. But then at each step, we decrease the rightmost number. When it's 0, we reset the rightmost number and decrease the left number. And if we count up the number of steps, this is 11. But like we could just add 1 at the beginning and everything's fine. And you can also do this for exponentiation. It's an interesting puzzle, so I won't spoil it here. But yeah. And then you can do something similar with equations. But there you use something called the bisimulation principle. However, like if you try to do that, then you get some diagram like this, where you need to relate all of these numbers. So so from this you might see that it doesn't really scale. So this is a commutative multiplication, and we didn't do the so we were able to do the Semiring properties, commutative Semiring properties, including this commutative multiplication, but we didn't do the exponentiation because of how complicated it would be. Okay, next approach.
That was all to address the termination issue. Is that what you were with the corecursor?
Yes, using the corecursor, then you don't need to explicitly do recursive call. So this will always terminate if you use this. Okay, next we have this embedded languages approach. So this is just the technique developed by Danielson. And here I just summarize the method for using it on like defining multiplication for Conatural numbers. So we define a type of expressions where we add the addition function as a constructor on expressions. And we also have this embed, which embeds like some nx, which are like head normal expressions. So you can take head to see whether it's nothing or just. But so crucially, this needs to be coinductive to allow for like infinite expressions or expressions with where you have plus and then it needs to be guarded by successor or it has 0. So here we can write 0 successor and then we allow this to be. And these two types are mutual. So this is actually something called a mixed inductive coinductive type. But yeah. And then we are able to define a function for Conatural numbers to these expressions just by corecursion, and also define a multiplication function that takes 2 Conatural numbers and returns that expression. And here you see we match on the predecessor of x and y again. And when neither of them is 0, then we have a recursive call here. However, now this is fine. Agda allows this because this plus and this embed are both constructors. No, in this language. But we've only defined this multiplication that returns an expression, so we need to interpret it into Conatural numbers. First, we define a predecessor function, which takes an expression and returns maybe an expression. This can be done just by recursion, structural recursion. So here, pred x and pred y are the recursive calls. And for this, a case for addition, you might also recognize this as when we have defined a naive version of addition. So it kind of duplicates the definition of addition here. And we also have this interp, which is just repeated applying pred E as like the stepping function for the recursion. But using this, we finally have multiplication. Okay. As like a example, we can look at like the trace of what happens. So the internal state is now the language that we have. Yeah, so from 4 times 3, if it decreases 1 time, it becomes 2 plus 3 times 3, and so on. Yeah, so we can also do the same thing with proofs, with the equations, where we define a language for them. So we have some embedding of this from some normal equations. And then we also have reflexivity, symmetry, and transitivity, and some congruent stuff. But okay, so when you interpret this language of proofs, then you also have some duplication because you need to re-implement this congruence of plus, for example. So there's an idea. So I have an idea that what if we just put all of the operations and proofs into a single language, or operations and equations into a single language? Then we don't need to separate these languages that have separate interpretations that duplicate stuff. So yeah, here we just quotient the language with the equations. So we still have the annex as before, and then we have this type of expressions where we have the addition, multiplication, 0, and then some equations. So we add all of the exponential commutative Semiring operations and equations. And we also have this embed and two equations that help us later. But so with this data type is actually, we can try this down in normal Agda. So our formalization is actually in cubical. And also in normal Agda, we cannot prove any non-trivial properties of coinductive types without postulating the bisimulation principle that I mentioned before. So yeah. Okay, so this is what I call a mixed higher inductive coinductive type, because this is a higher inductive type and that's mutually coinductive. And what makes it weirder is that these two constructors the type of these two constructors depend on the structure of that coinductive type. Okay. Next, using inside this language, we can define again the predecessor function, and here everything is by recursion, and now the definition the definition of addition and multiplication look basically identical to the naive version. So, but Agda accepts it because everything is a constructor. And also, I mean, it's not even coinductive, or not even corecursive functions, so it's fine. So even for proofs, you can also use transitivity and everything. Okay, having this, we can again define the interpretation function using the pred. But thanks to the two constructors that I added before, so these two constructors relate the predecessor function with either 0 or 1 plus value. So using these two constructors, we can actually prove a round trip. So we can embed Conatural numbers into expressions, and then we can prove the two round trips. so expressions are actually isomorphic connection numbers. And so how do we get all the operations and equations? We first define like a record that contains all the operations and equations. We trivially have all the have an instance of this record for expressions, and then we can just use this isomorphism. And in Cubical, we have this univalence axiom where we can transport over equalities or isomorphism. So from this we get this automatically from just one line. Yeah. Although actually you can also derive this without univalence. However, it's much more work. You need to do stuff for every field that I have in this record. Okay. So in conclusion, we have formalized Conatural members forming an exponential commutative Semiring in cubical Agda, and this is also like a showcase of a practical application of cubical Agda and also univalence. So we tried like different approaches. One using corecursion and bisimulation, which I didn't go too far into, but here we proved that Conat from a commutative Semiring, and it doesn't scale. Next we used this quotient embedded language, and we proved everything that we wanted. However, there's one problem that it's not modular. So we have this huge data type. However, if we want to add more operations or equations, we must modify the data type and modify the whole proof. Okay, so there are some open questions. Like, is there a way to prove this that is both simple and modular? So simple like the second approach, but modular, or like the first approach where we didn't rely on anything. Okay. Another question is like, is there a way to define more complicated functions like titration or like the Ackermann function? Like, it's not clear what kind of internal state or what the predecessor of like titration of two numbers is. And then lastly, so I use this mixed higher inductive coinductive types. However, this is another one of these crazy data types that Agda supports. So we are actually not sure what the semantic justification of having these are. Yeah. Okay, and this is it for my talk. Thank you.
Using Gaussian time theory to model these functions, or maybe Gaussian.
Right. So there are like these fancy extensions of type theory, like guarded type theory, or like also size types, which might help with this. We didn't consider those. We try to just do like, okay, not as vanilla like that because this is still pretty fancy like that, but yeah.
I think that's the combination property is explicitly discussed in the literature of Gaussian type theory. That's they claim that is the co-inductive type theory could be modular. Because we only one implementation and have to try that. So.
Yeah.
You mentioned that Agda doesn't
right?
Maybe beyond the scope.
It's the same reason that you don't have function extension. Yes, in cubical like that we can prove all of these properties. Like we can also prove the bisummation of this. Yes.
in cubical like this, are all infinite conads equal?
Yes. Yes, so the elements of connatural numbers are just all the natural numbers plus infinity. However, this is not actually isomorphic to net plus one.
Question, you're doing the proofs on the quotient language.
Yeah.
Was that pretty much like normal syntax of proofs in Agda, or was it like more verbose than usual? I'm kind of thinking of some of the things I've done, and I ended up with some very verbose proofs.
You mean
That's just this? Or no, like proofs about the equations. Like,
oh, yeah, I didn't think to them. Oh yeah, I had this, but I'm lagging here a bit. So
okay.
yeah.
So is this is for the quotient?
No, so I have like omitted a lot of stuff here,
Right.
and also like this doesn't actually fit with this.
But like, so for the quotient one, is the proof, do they look similar or are they quite a bit different? Like,
No, it's actually basically the same as the naive one. So all of the proofs and operations that are here are the same as naive one. So that's like an advantage of this one.
To deal with the coherence problems, coherence computations.
So you can also add an is set here as a constructor. Yes.
Zero. I don't need to do induction over explain.
You're doing recursion or also induction is a one dependent predecessor. Switch to oh yeah, this stuff is the function that we are defining currently, and when this is called co-pattern matching. Where we
So I thought that it was like these are only
yeah, x minus one below are variables. So x minus one here is variable that you get from.
set truncated.
Yes. So this is actually set truncated.
Where do you need the line B? Where do you need in the that it is a set?
Yeah.
Visualization or somewhere.
So so to derive the isomorphism, I had to like prove some equations about this Pratt function, and there I use UFD.
And if you don't have this, you can still define the commutative Semiring structure, or do you need UIP?
Probably it doesn't need a set truncation.
But wouldn't you get into trouble when you're defining Freddy over the equations? Because that means that those are also respecting the equations if you're not in a set.
So here that is fine because that is you do the same thing when you prove the equations using the naive method. You are trying to you are proving that they preserve the Pratt function or the predecessor, and here you are doing the same thing.
that will finish up our Q&A for now. And of course, thank you very much.